Last lecture we have seen that there was a 2 by 2 matrix which was given to you, which was A. Then we wrote, after that we wrote eigenvector matrix S. We multiplied. We found that the multiplication was exactly equal to eigenvalue, eigenvector matrix multiplied by diagonalized eigenvalue matrix. Now this was obvious. This happened in 2 by 2, as well as we have cross-checked that it happens in 3 by 3. Now these eigenvectors which are sitting here, let us call them x1 and 2. These are the eigenvectors. So what we said, what do we mean by eigenvectors? We said matrix A multiplied by eigenvector x1 should give me eigenvalue times eigenvector. That is what our understanding about eigenvector was, right? So if x1 and x2 are eigenvectors sitting in these two columns or whatever number of columns, then that matrix and matrix in RHS, it is exactly same. So x1 and x2 are also sitting here, right? And therefore this equation, if we are applying for first vector, that means A times x1, so matrix A vector x1, which looks like this, will be equal to lambda 1 times vector x1. If we apply it to vector x2, it will look like lambda 2 times x2, right? And then when we combine both of them, it looks like this, because anyway at a time one vector is being multiplied to the given matrix, and therefore what you end up getting, I mean, if you want to write down multiplication which is present in RHS, we can always write it down as sigma 1 times x1 plus sigma 2. That is what is your RHS. These are vectors, these are scalars. And because all other entries x1 multiplied by lambda 1 plus x2 multiplied by 0, that is what is vector multiplication, I mean row into column, and this is what is your RHS, and therefore we are bound to get A into eigenvector matrix S is equal to eigenvector matrix into capital lambda, which is diagonalized eigenvalue matrix, diagonal matrix. Now, only thing that you need to take care of is, if you are putting lambda 1 in the first position of diagonalized matrix, then corresponding eigenvector must be there in the first position of eigenvector matrix. x2 is in second position, then corresponding eigenvector matrix must be there in the second position, and so on. I mean, this is 2 by 2 example, 2 by 2, 2 by 2. But even if it is n by n example, this thing must be followed. Then you will get this expression, which is very important expression. And because if matrix A is non-singular, if determinant of A is not equal to 0, we can always multiply. Okay, and if determinant of A is not equal to 0, then eigenvector matrix S determinant also will not be equal to 0, and hence there will exist S inverse, right? So from this equation, if I multiply both sides of the matrix equation by S inverse, we get S lambda S inverse. And if you look at RHS, S into S inverse, as the multiplication is associative, this is identity matrix. That means it is A is equal to eigenvector matrix into diagonalized eigenvalue matrix into inverse of eigenvector matrix. So this is factorization or decomposition of matrix A. So you write down any matrix A, let us assume that it is non-singular. So there are enough, whatever is the dimension of that matrix, there are linearly independent that many vectors available. So if it is a good matrix, then that matrix can be factorized or decomposed in this fashion. Find out eigenvectors, diagonalized eigenvalue, and find out inverse of eigenvector matrix. This is what is going to be your decom, and this is the characteristic or character of your matrix. And that is why eigenvalues, eigenvectors are also called characteristic values or characteristic roots or characteristic vectors. So this is the backbone of your A. Eigenvalue matrix multiplied by eigenvector matrix multiplied by diagonalized eigenvalue matrix multiplied by S inverse. So this is going to be very useful to you as far as dealing algebra of matrices is concerned. Okay. Now, what is the application? Application also we have observed that when we multiplied A by A, we got a square whose eigenvalues were lambda square, lambda 1 square, lambda 2 square, whatever eigenvalues were of A, corresponding square eigenvalues were for A square, and actually
excuse me,
yes,
sir, एक the last sentence repeat करता का ते, that's why eigenvalue
characteristic. This is the this RHS really talks about characteristic of matrix A. The backbone, the skeleton of A is available in RHS. Essentially, the eigenvector matrix and eigenvalues. Those are the important characteristics of matrix A, which we find out. And why eigenvectors? Because they are invariant. They don't change their positions. They don't change their positions. Their position in domain and codomain, they are exactly same. That is why it is a character. I mean, you can get different numbers in the matrix A, but then if the eigenvectors and eigenvalues are same, their factorization is going to look like this eventually, decomposition. Okay, we are talking about applications. So if I do A square, I observe that eigenvalues are correspondingly squared, whereas eigenvectors continue to remain same, A square. And it is true for n, because now why? Let us, I mean, that proof is obvious from the above expression. If A is equal to S lambda S inverse, then A into A is equal to S lambda S inverse into S lambda S inverse. Correct? So that is what is your A square. This 2 produce identity matrix and therefore it disappears. These are the diagonalized two matrices. So lambda into lambda, and therefore it becomes lambda square S inverse. Okay. So as far as eigenvectors of A square are concerned, they are the same. As far as eigenvalues of A square are concerned, they are doubled. They are, I mean, not doubled, they are raised to power 2. And therefore, If you do for n where n is a natural number, then a raised to n also will eventually give you expression S, which is eigenvector matrix lambda raised to n S inverse. Okay. So this is the first application of decomposition of the matrix. Now, can you find out eigenvalues if, okay, let me write down the question correctly. If lambda represents eigenvalues of A and S represents eigenvectors of A, and if determinant of A is not equal to 0, then find eigenvalue lambda and S of A inverse. What do you think will be the eigenvalues and eigenvectors of A inverse, and why? Okay, A is equal to S lambda S inverse. So if we take inverse of both sides, A inverse is equal to S lambda S inverse. While taking inverse or transpose, reversal law applies, and therefore sequence of all matrices is flipped. So S inverse lambda inverse S inverse, which becomes S into lambda inverse into S inverse, which is A inverse, and this is in the same form, and therefore eigenvalues of inverse A inverse are reciprocal of eigenvalues of original matrix. That is what we have acted. Okay. Now we will keep working on this today. Therefore, what I want you to do is get me that 2 by 2 matrix, which was 5 minus 2 minus 2, 2. This was our A, and I values were lambda 1 was 6 and lambda 2 was 1. So what was the characteristic equation of this matrix? Characteristic equation of this matrix was simple, 5 minus lambda minus 2 minus 2, 2 minus lambda, determinant is equal to 0. So lambda square minus 7 lambda minus 7 lambda minus how much? 5 गुणे 10 10 वजा 4 6. This is our characteristic equation. Okay. Now let us write this equation. 5 minus 2 minus 2 2 square minus 7 times 5 minus 2 minus 2 2 plus 6 1 0 0 1, because if it is a matrix equation, all of them should be matrices. Multiplied by scalar is fine. So find out RHS of this. Okay, if you do the calculations correct, you will end up getting matrix 2 by 2, but all entries 0, 0, 0, 0. I can ask you to do it for 3 by 3 also, but then it will be too much of calculation for you. Therefore, this observation is saying that every matrix satisfies its own characteristic equation. This is what is the statement we will observe by doing couple of trials. I have asked you to do only one trial, and then if this statement is going to be always true, then it is of course theorem, and the name of the theorem is Cayley-Hamilton theorem. Check if you can prove it. Prove Cayley-Hamilton theorem. How do we get the characteristic equation of any matrix A? We A minus lambda I, determinant is 0. That is how we get the, this is what is the characteristic equation. This is given to us. Okay, so one characteristic, so it's a characteristic equation of matrix A. And we want to check whether every matrix satisfies it or not. What she has done is she put A minus AI, put in place of lambda A, and check what happens. Is that equal to A minus A determinant equal to determinant of 0, which is 0. That is what is her proof. But so shall we accept this? Yes or no? And if no, why no? That is my first question. And second question, how do we actually prove it? Yes or no?
Sir,
One thing which I know, let me show it to you. Lambda, say, let us take the first one, lambda square, 7 lambda plus 6 is equal to 0. And suppose we have a matrix A, whose eigenvalues are lambdas. I mean, couple of them. In this case, it will be 2, lambda 1 and lambda 2. And there will be corresponding eigenvectors x1 and x2. Okay, so we know this relation. Ax1 is equal to lambda 1 x1. Ax2 is equal to lambda 2 x2. Okay, these relations are known to us. So if we multiply this polynomial by vector lambda 1 lambda 1 x1 lambda 1 square x1 minus 7 minus 7 lambda 1 x1 plus 6 x1, is this equal to 0? I mean, now this is a vector equation. Vectors, x1 is a vector. Can we say this from, if this is given to us, lambda square minus 7 lambda plus 6 is equal to 0 is given to us. So we take out the eigenvector of A and multiply it throughout LHS and RHS. Of course we can do. Now lambda square x A square x 1 was lambda square x1, we have already proved this earlier. That is what the work which we have done now. So I can always substitute this fellow by a square x1 because of these properties. I mean, this is for 1, but I can always write couple of steps where powers are more. For 7 lambda 1 x1, I can write 7 ax1, and for 6 x1, I can write 6x1, 6ix1. Okay, which is equal to 0. And then I take out that x1 which I had borrowed. I get a square minus 7a minus 6i. This is the matrix multiplied by x1 bar is supposed to be 0 bar. But x1 is our non-zero matrix, non-zero vector, because we have said that it is non-zero eigenvector because eigenvalues are real. Lambda 1, lambda 2, x1s are non-zero vectors. So if this is a vector equation, then x1 is not 0. Therefore, a square minus 7a minus 6i is equal to, I mean, this is, I don't think this is complete proof, but this gives us idea about why Cayley-Hamilton theorem is correct, and it is going to be true for x2 also. And if it is going to be true for x1 and x2, it is going to be true for any corresponding linear combination of x1 and x2. So it will be true for all vectors in that space. I think this is good explanation. Check if you have any objections. Okay, we are not proving Cayley-Hamilton theorem. We are not getting into details of the proofs because, but we verified that it works for if you substitute capital A, that is matrix, in place of lambda, it satisfies the characteristic equation. And that property or that theorem, even if unproved, might be useful to us in getting some value of high degree polynomial in matrix A, like I am demonstrating here, a cube minus 12a square plus 15a plus 7. If you are supposed to report the value of this, A maybe is given 2 by 2 or 3 by 3 to you, then this problem will take 15-20 minutes for you to actually find out a cube, a square, a, and then determinant of this is us, suppose overall determinant of this matrix is us. Then it will take huge time for you to do it. But then if you could decompose this matrix equation into the matrix equation looking like characteristic equation, then you can substitute those zeros over there and you can reduce your work. So that is where we will use Cayley-Hamilton theorem for simplifying our algebra. We are not getting into the proof of Cayley-Hamilton theorem. We will use it. Okay. Next thing that we would like to do is, suppose this is your matrix P, whose inverse we have already found out. So P inverse also, let me write down. If it is wrong, you correct me. 1 by 2 minus 1 by 2, 1 by 2 minus 4, 3 minus 1, 5 by 2 minus 3 by 2 and half. Okay. This is P inverse. We have got a 3 by 3 matrix whose eigenvalues were good. So let A, matrix A be 1 minus 1 0, 2 3 2, 1 1 2. Okay, and corresponding eigenvalues of A where lambda 1 is equal to 1, lambda 2 is equal to 2, lambda 3 is equal to 3. Uh, I want you to find out eigenvalues of eigenvalues of P A P inverse. That is 0 1 2 1 2 3 3 1 1 into 1 minus 1 0 2 3 2 1 1 2 into half minus half half minus 4 3 minus 1 5 by 2 minus 3 by 2 1 by 2. Find eigenvalues of this product, whatever that matrix you will get, find eigenvalues of that product. Okay, so actually the sequence of this P and P inverse should be opposite. So we are not trying this out, 3 by 3 multiplication. It should have been P inverse AP. So if you have patience, you can calculate this and then find out the lambda values of certain matrix. But why I was asking you to do that was we wish to prove this statement. Two matrices A comma P inverse AP have the same characteristic roots. It can be proved very quickly, very easily. Okay, let us try to prove this. A is a matrix whose characteristic root is lambda. So Ax is equal to lambda x is known to us. Now we are supposed to go to P inverse AP and say that it also has the same characteristic root. So let us multiply it by P inverse. Ax is equal to P inverse lambda x, which is equal to lambda is a scalar, so it can go outside. You get P inverse x. Okay. Now P inverse A, we want P. Therefore, we multiply by P inverse x. So this is identity. So this and this is LHS is equal, which is equal to, so we have got lambda times P inverse of x. So if P inverse AP is suppose your matrix B times P inverse x, a vector, is equal to lambda times same vector P inverse x. Therefore, matrix B has got same characteristic roots. Okay, and matrix B has, this is eigenvector of this. This is eigenvector of P inverse AP. Lambda will be eigenvalues of P inverse AP, and P inverse X will be eigenvectors. Good. Next. I mean, it can be done more than one way, so we are just demonstrating by one method. If A and B are two square matrices, next, if A and B are two square matrices, then the matrices AB and BA have same eigenvalues, characteristic roots. Try to prove this statement. AB is equal to B inverse BAB is equal to B inverse BAB. These are the two watchmen. I mean P inverse AP. That is what we have proved in this theorem. P inverse AP and A, they have same characteristic roots, and this is exactly same. Therefore, AB and BA have same characteristic roots. चालेल का रे? Characteristic roots of triangular matrix. Are the diagonal elements of that matrix. कंटाळ्यात की सांगा. If you take matrix A as A11, A22, ANN, and you have all the above entries available there. These entries are there, yes, and these entries are 0. Then what will be the characteristic equation of this? A11 minus lambda into A21 minus lambda. I mean, you will expand it like that only, na? Dot 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 A22 ही थे into ANN minus. This is what is going to be your polynomial expression. If you equate it to 0, this is what your characteristic equation, right? And all the diagonal entries will make it 0. Therefore, they are characteristic roots. नाही समजत आहे. 1 1 1 A22 A33 आपण इथे काहीतरी नाव देऊन टाकूया. XYZ 0 0 0. Okay, so A11 minus lambda 1, A22 minus lambda, A33 minus lambda. Now if we expand this determinant with respect to first row, what it will be? A11 minus lambda times multiplication of these two minus 0, A22 minus lambda into A33 minus lambda. Okay, minus 0 is gone. Now if you expand using x minus x inside bracket, 0 into this, 0 into this, 0 plus y inside bracket, 0 into 0, 0 into 0, 0. So basically your determinant is this first diagonal entries only. That is why it satisfies. Okay. Now last statement, and then we will do something else. Last statement in this series is characteristic roots of idempotent matrix that is A square is equal to A type of matrix, either 0 or 1. Why? Now A square is equal to x, A square is equal to A, therefore we can always write, by doing some algebra we can always come to conclusion that lambda square is equal to lambda, implies lambda is equal to 0 or lambda is equal to 1. Now definition. Maximum number of speed linearly independent rows of matrix is called row rank of matrix. Maximum number of linearly independent columns of matrix is called column rank of matrix. The largest non-vanishing subdeterminant of a matrix is called determinant rank of the matrix. Okay, it's simple. I mean, if you have been given a system, if you have been given a matrix, you row reduce it, find out how many linearly independent rows are there. That is going to be row rank of that matrix. Find out how many linearly independent columns are there. That will be column rank of the matrix. And if you find out the largest non-vanishing subdeterminant, the size of that is the determinant rank of that matrix. Fundamental theorem of linear algebra. System will have solutions. If and only if row rank is equal to column rank is equal to determinant rank. Now, let me explain you this by taking examples. Okay. Let us take a simple example which we can visualize also and get to know about this rank also. Suppose we have two equations, a11x plus a12y is equal to d1, a21x plus a22y is equal to d2. So our matrix A will look like a11, a12, a21, a22. Okay, and then while row reduction, if we want to solve them simultaneously to get the values of x and y, the row reduced echelon matrix, if we want to consider, then we consider the matrix which is, let us call that as D, matrix D, which is row reduced augmented matrix, row reduced echelon matrix, which is augmented from the RHS. Also we have a dotted line here, A21, A22, D2. Okay. Now, rank of A is denoted by row of A. Rank of D is denoted by row of D. Case 1. Row of A is equal to 2 and row of D is also equal to 2. What do you think will happen? This is case number 1. Is it difficult? Determinant rank. Let us discuss about the determinant rank. Determinant rank of A and determinant rank of D. Suppose both of them are 2, 2. That means the largest non-vanishing subdeterminant of matrix A has a size 2 by 2. That is the meaning of row of A is equal to 2. That means it is non-singular matrix. Capital A is non-singular matrix. It is non-vanishing. That means it does not become, determinant does not become equal to 0. So if this rank is 2 and rank of capital D, that means augmented considering RHS also, if it is 2, the largest non-vanishing subdeterminant of D is also 2, then it is good system. Now, just try to think this corresponding to what we have already learned in solving simultaneous equations. So, the meaning of this row rank, determinant rank of A and determinant rank of B, they are equal and full rank. Basically, 2 by 2 we are solving right now. So, full rank. Then, as far as solution is concerned, it's a unique solution. Lines are, these two lines intersect in the point. Lines intersect in a point, and that means that is there is only one point which satisfies both these equations, and this is very intersecting, a very happy situation. Case 2. Case 2, you have row of A equal to 1 and row of D equal to 2. Now how will you interpret? Now if you want numerical example for the first, we can always write, say 3x plus 2y is equal to 5, x minus y is equal to 0. Okay, let me just explain you this particular thing. 3, 2, 1 minus 1, that is our A, and D is 3, 2, 3, 1, 2 minus 1, augmented 5, 0. Now this 2 by 2 determinant is non-zero, therefore rank of A is 2, correct. Now try all 2 by 2 here, and if you happen to get only one non-zero, still rank of this is 2. बरोबर है. So all the 2 by 2 determinants of D, 3, 1, 5, 0 is non-zero, 3, 1, 2 minus 1 is non-zero, 2 minus 1, 5, 0 is also non-zero. Therefore all the 2 by 2 determinants of D are non-zero, and therefore rank of matrix D is 2, determinant rank, and therefore we conclude that lines intersect in a point. Why? Because we know they intersect 1, 1. But then every time, if it is n and m dimensional systems, we will not be able to cross check by actually solving them simultaneously. We will have to predict what is going to be the solution set. Is it a point, unique point, or is it a line, or is it a plane, or is it a space, or is it a 5-dimensional space, or is it a 7-dimensional space? We should be able to predict what is the dimension of solution set. That is what we are doing this exercise, and that is why new term rank of the matrix is in picture. Okay, so now the situation is row of A is 1 and row of D is 2. Okay, so what will be that situation? I want this 2 by 2 determinant to be 0, so I will take these equations like this: x plus 2y, say, is equal to 3, and 2x plus 4y is equal to, if I write 6, then it is a different story, but I write 5. Then my matrix A is going to be 1, 2, 2, 4. Matrix D is going to be 1, 2, 2, 4, 3, 5. So largest non-vanishing subdeterminant of D has size 2 by 2. This determinant is not vanishing. Therefore, rodeo is 2. However, 4 minus 4 is 0. Therefore, largest subdeterminant of matrix A, which is vanishing, is 2. I mean, non-vanishing is 1. Therefore, this is 1. Okay. So, what is the situation? What is the interpretation of this situation where row of A is 1 and row of D is 2? I mean, there is no solution. And what is our geometric interpretation of these two lines? They are parallel lines. No solution. Okay. Now, and case 3. Row of A is 1 and row of D is also 1. What does it mean? It means, suppose I would have put, instead of 5, 6 here, then A is 1, 2, 2, 4 and D is 1, 2, 2, 4, 3, 6. So determinant rank of D is also 1. This is also 1. Then you have a solution. That is what is fundamental theorem. You have a solution, and then if the dimension of this matrix is 2 by 2 and your rank is 1, then you have a one-dimensional solution set. Therefore, they are coincident lines. The line is the solution set. One-dimensional. Now this is easy in case of two equations. So let us make it little difficult so that we understand it completely by taking 3 by 3. So this is over. I mean, a couple of more cases if you want to do. Rho A is equal to 0, rho D is equal to 1. That means, rho A is equal to 0 means all the entries LHS are 0, and rho D is equal to 1 means one of the entries in RHS is non-zero, which is 1. Of course, there will not be any solution set in that case. And the last case will be rho A is equal to 0 and rho D is equal to 0. That means everything is 0. In that case, you have 2 by 2, the entire plane is a solution set. So those are the two cases where empty set and solution. Maybe we can write case 4, rho A is equal to 0 and rho D is equal to 1, and rho A is equal to 0 and rho D equal to 0, case 5. Now why am I not taking rho A greater than rho D? Because it does not make any sense. It doesn't make any sense. Rho A cannot be greater than rho D because D contains A. Okay. So if rho A is 0 and rho D is 1, then no solution. And if rho A is 0 and rho D is 0, that means everything is 0. All the entries are 0. Solution set is R cross R. So these are the two important cases of our Ax is equal to B, which we were trying to ignore because now they are too easy to understand. The other things are this. Whenever, now you observe, whenever this is equal to this, you have a solution set. Whenever you have this is equal to this, you have a solution set. That is what is our fundamental theorem of linear algebra. Now let us do it for 3 by 3 and check whether we understand these things. Okay, so now simultaneous equations. A11x plus A12y plus A13z is equal to D1. A21x plus A21y plus A22y plus A23z is equal to D2. And A31x plus A32y plus A33z is equal to D3. Right? Corresponding A is A11, A12, A13, A21, A22, A23, A31, A32, A33. Corresponding D is A11, A12, A13, dotted line D1, A21, A22, A23, dotted line D2, and A31, A32, A33, dotted line D3. This is your augmented D. Now cases. Case 1. Row A. अरे मगाशी मी रो वेगळा काढला आता रो वेगळा काढतो. Row A is equal to 3 and row B, row D is equal to 3. What do you think? It is very simple. All the three planes. Now we are talking about this plane. These are planes. So interpretation is easy. Three planes intersect in a point, O point. So that is what is a unique solution. Case 2. rho A is equal to 2 and rho D is equal to 3. Tell me. Now you visualize and tell me what is this situation. Rho A is 2 and rho D is 3. Pause. Determinant of 3 by 3 is 0. But if you take any subdeterminant, some of them, not all, but some of the subdeterminant, at least one of 2 by 2 subdeterminant is not 0. So geometrically, it is going to be like this. Three planes are going to be such that they form prism. Okay, to intersect, and the intersection of second, I mean, all these lines can be parallel. All these lines are going to be parallel. Okay, and what you were considering is a special case. Many of you have shown me the answer that these two planes are parallel and there is a plane which intersects these two. That is the case that you were telling me, which is also correct because it is a special case of prism where these two parallel planes intersect at infinity. So these two parallel lines and the other line also is going to be parallel to these two. So it's a prism. So this is a prism. They both of them are same, and that is what is this situation. Prism. Planes form prism. So no solution. And anyway, 2 is not equal to 3, therefore no solution. Case number 3. Rho A is equal to 1 and rho D is equal to 3. What can you conclude out of this? This is not impossible event. Because if I want the rank of A to be 0, 1, then only what? One entry non-zero if I put, then I will get the rank 1. So I can consider all of the remaining ones as zeros. So all the zeros will come in this and they will not allow you to have rank 3. So if you have rank of A is 1, then rank of D can maximum be 2. 3 is impossible. Check whether you understand this. This is impossible event, not possible. Case number 4. Let us improve on rho A. Rho A is equal to 2 and rho D is also 2. This is easy. This is easy.
Can you explain the case 3 again?
Case 3 again. Can we create an example where rho A is 1 and rho D is 3? It is impossible to create that example itself because I can create rho A is equal to 1 by saying 1 0 0 0 0 0 0 0 0. Okay, or too many zeros. If you don't want these many zeros, then you can consider 2 rows 0. Delete. Okay. Worst come worst, what we can have is say 1. Suppose we have 1 1 1 0 0 0. Still we have, what is the rank of this? Any 2 by 2 is also 0. All 3 by 3 are 0, and only 1 is non-zero, therefore rank of this is 1. But then the moment you put this vector, this matrix along with d1, d2, d3, you are not going to get 3 here. That is what it means. because either one of the entire column or one of the row is 0, then and then only it is going to be possible to have row A 1. So I mean, more than this, I just cannot explain. We'll have to take the examples and try to create, and we will fail to create. If we add D1, D2, D3, and A has all the same entries that of A, so these three guys, these 3 by 3 is going to produce row A1 only, but suddenly we want 3 by 3 matrix to produce non-zero 3 by 3 determinant, which is not going to happen.
Yes, sir.
Okay, so if rho A is 2 and rho D is 2, what do you think is going to be the solution set? And what is the geometry of that solution set? Is it easy? Rho A is equal to 2 and rho D is equal to 2. That means, bola. This rho A is equal to 2 and rho D is equal to 2 is possible when the planes are coaxial. They have a line in common. Now, that is what I am saying. Maybe you try to take the numbers over here and try to figure it out. You will end up saying that yes, there is a line which must be common between these two. And therefore, solution set is dimension 1, straight line, which matches with our earlier requirement that dimension of matrix A is 3, it's a 3 by 3, and the rank is 2, which is equal to 1 dimensional solution set, which is correct. When the dimension of the matrix is 3 and the rank of A is 3, 3 minus 3, 0, therefore dimension of solution set was 0, it was a point. Case 5. Rho A is 1 and rho D is still 2. What does it mean? It means 3 planes are parallel. You can cross check this. Therefore, there is no solution. Case 6. Rho A is 1 and rho D is also 1. What does this mean? This means all 3 planes are coincident. Okay, and therefore if all 3 planes are coincident, rank of row A is 1, size of A is 3 minus 1 is equal to 2. So solution set has 2 dimensions. If you row reduce this matrix, you will end up getting only one pivot, some B1, some B2, 0, 0, 0, 0, 0, no other pivot. And of course in RHS you will have D1, 0, 0, and therefore this is the solution set. 2-dimensional. You can have your Y free, you can have your Z free, and therefore 2-dimensional solution set. The plane itself, the given plane itself is a solution set. Now these are the 6 different cases. Maybe if you want to add 2 more, case 7, rho A is equal to 0, rho D is equal to 1, and case 8, rho A is equal to 0 and rho D is equal to 0. This is going to be empty, so empty set, because in RHS D1, D2, D3 you have one entry 0, that makes rho D 1, and rho A is 0, that means there is no entry in these 9 entries which is non-zero, everything is 0. Therefore, there is no solution set. And when rho A is 0 and rho D is also 0, it is nonsense business. Everything is 0. This is how D will look like. And R cross R is the solution set, complete solution set. That completes the story of what do we mean by rank. From rank, how do we arrive at the dimension of the solution set? If rank of the matrix A and rank of matrix A augmented D is same, then and then only the solution exists. Otherwise, there is no solution. These are the things that we have analyzed by analyzing these 2 lines simultaneously and 3 planes simultaneously. That is what is the content for today. That is where we stop for the day. I will keep this board open for some time but stop recording.